All right, now I'm going to give you what's probably the most instructive example of something called the washer method here. It's a fantastic problem. So let's go ahead and cruise over here. We're going to discuss something called, just really quickly, am I still good? I'm in a good color. The washer method. And I'll explain why it's the washer method. All right, now, you ready? Here we go. I want to find the volume. You kind of gotta key into how these things are written to understand what you need to do and when. After you've seen a few of them, it comes pretty easily. But let me write this up. Find the volume of the solid created when the region bounded by f of x equals root x and g of x. I don't know if you can hear that screaming over there, but Carter's going off on his kids. It's awesome. Is, and then we're going to do A, and we're going to do rotated around the x-axis, and B, rotated around y-axis. Okay, so the first thing that we're going to want to do is let's get a look at what we're really talking about here. Okay, so let's try and figure out what's going on. I've got the region bounded by f of x equals root x. All right, let's change colors. Let's go f of x equals root x, which we know looks like this. So this is f of x equals root x, right? And then we've got g of x equals the cube root of x. So this is g of x. Did I say cube root? I'm sorry, I meant x cubed. So the region bounded is this guy in here. Now we'll just do it like this. This guy is going to be our region, right? Now, let's take this real slow and real easy, all right? Because this can get a little confusing because we got a lot of stuff going on and we're going to do these in separate parts. I want you to notice the difference between this problem and the problem that we just did over here when we took just root x and went around. Do you notice that my region, if you think about it, I took root x from 0 to 4 and I went around the x-axis, and what I really did is I took all of this region in here, right? There was no hole between the action, here's my action slice, and my axis of rotation, right? But look over here, there's a hole. In other words, if I take, let me change colors again, if I take an action slice, that sounds so funny to say, if I take an action slice, so there's my little action slice, remember this thickness is delta x, and this height of this guy, if you look really close, is f of x minus g of x. I guess technically I should write it as x sub I and g of x, or excuse me, f of x sub I and g of x sub I, right? So this is going to be for our ith interval. Do you notice, though, that the bottom of this rectangle, there's a hole between the axis of rotation, which is the x-axis, we're doing A first, and the action. So the question is, how do we deal with that? And the answer is actually, it's pretty straightforward. Think about it this way. What I do is, I will carve out that same kind of half watermelon looking thing that I did for the previous problem. And then what I'm going to do is I'm going to come in and I'm going to carve out the center of it. And what I'll be left with is this little area right in here. I guess it's not an area, it's a volume. So it's kind of like a lathe. I don't know if you guys know what a lathe is. It's kind of wait, let's be clear. This little circle area, when I said that we're left with that, that's not what we're left with. We're taking this out. We're lathing that out. What we're left with is this thing going around through 360 degrees. So we end up with almost kind of like this crazy looking, it's like a crazy looking bowl, right? That looks like this, but it goes through 360 degrees. And it's empty on the inside. It's like we got this little funnel bottomed bowl or funnel inside bowl. Okay? I want to make sure I was clear on the way in which I described that. All right, so let's go really easy. Think about how this would work. Well, I'm going to take the outside volume first, and then I'm going to carve out the inside volume. Well, that's easy enough, right? I know that the outside volume is simply going to be pi. We just did it. It's pi times the integral from 0 to, ooh, I should probably find out what I'm bounded by, right? So let's change colors one more time. And what are these points? Well, hopefully you've played enough with these types of functions to realize that they're going to intersect at 0, 0, and 1 comma 1, right? Because 1 cubed is 1, square root of 1 is 1, etc., etc. So I know this is going to be the integral from 0 to 1 of, now I'm not going to get too crazy yet, I just want to talk about this. It's going to be the square root of x squared. I'm not going to do dx yet because I want you to think about this and see if we can do this in one fell swoop, as it were. I'm going to carve out the inside of this thing, right? And I'm going to be left with the shell, the husk on the outside. Well, how do we carve stuff out mathematically? How do we remove things mathematically? Well, we subtract. So when I subtract this, I'm going to get x cubed squared. So what we need to do is we need to think about this in another way. And I need to draw this bigger so we can really see what's going on. Not bigger, just maybe more room over here. All right? So let me draw this, and then, of course, I'll add my dx over here, but let's be sure. Okay, so think about it this way. There's square root of x, and then here comes x cubed, right? Can you think about it this way? This is my outside radius. This is going to be my big radius, which is squared right here. This is r squared. And then what do? Well, I subtract out my inside radius, which is, if I change colors real quick, my inside radius is this guy right here, squared. You see how that works? Now, you may say, wait, but Ripley, the height of this thing is f minus g of x, right? So why wouldn't we square that? Well, because there's this hole between the axis and the action, or the action and the axis of rotation. Again, if I draw this little slice of action right here, my outside radius is this big guy right here, and then my inside radius is my little guy right over here. This is my little r of x. All right, so we need to think of it as outside radius squared minus inside radius squared, because we're literally carving out the volume of the solid created when I rotate x cubed from 0 to 1 around the x-axis. All right, now again, if we thought about this, we know that the integral of a sum is the sum of the integrals. So I could just as easily say, okay, this is going to be pi times the integral from 0 to 1 of the square root of x squared dx. Well, what does that give us? That gives us exactly the same thing as this one, only instead of from 0 to 4, it's from 0 to 1, right? And then what do? I subtract out, I subtract out pi times the integral from 0 to 1 of x cubed squared dx. So what is that? Well, that would be the same thing as if we took x cubed from 0 to 1 and rotated it through 360 degrees. Ooh, this is really hard to draw on this tablet. Sorry, you guys. Right? So if I take and subtract out all this garbage in the middle, what I'm left with is this guy. All right, now I'm actually going to do this one out by hand so we can see what it is, because I want to show you something, which is really cool. All right, I'm going to have pi. Now I'm going to go back up to this one if you guys don't mind, because I'd rather do one step rather than two. The integral from 0 to 1 of x minus x to the 6th dx, and this is equal to pi times x squared halves minus x to the 7/7, and this is from 0 to 1, so this ends up being pi, let's see, times 1/2 minus 1/7, which is what, 5 pi 14ths? Is that right? 7 minus 2 is 5 pi 14ths. Okay? Okay, sorry about that. Somebody was at the door. Now, let's think about something for just a sec, because I want to make sure everybody understands this. Why is this called the washer method? Why are we talking about washers? Well, if I take this little sliver and I go through 360 degrees, can you see that what I'm going to get is I'm going to get a washer looking thing. It's almost as though I took my hockey puck, remember, from the disc method, It's almost like I take my hockey puck, while my drawing is getting worse and worse, isn't it? And I cut the middle out of it. So I end up with this washer-looking thing. When I count up an when I count up an infinite number of infinitely thin of these hockey pucks with a hole in the middle, they end up looking very much like a CD, right? If you were to look down on them, it would look like a washer. That's what it would look like. I stack all those up, I add up an infinite number of infinitely thin washers, and I get the volume. Now, let's look at part B. Let's see if we can build part B if we go around the y-axis.